Sometimes bad things happen to good CAD models. Sometimes you change one dimension and the whole thing blows up. Or maybe you change something and you have to go back in and fix a bunch of dimensions just to get everything back the way that you want it. Well, either way, this probably could have been prevented with a little attention to design intent. I'm not talking about a huge list of best practices that you need to memorize. I'm just talking about a way of thinking that guides you to more robust, maybe even bulletproof CAD models. This means your designs behave the way you expect them to. They update reliably. They don't fall apart the moment you change one little dimension. So let's take this one step at a time. We're going to start with 4 questions that you can ask yourself as you design, and then we'll take a fragile part, one that I set up to break easily, and then we're going to make it practically indestructible. So the first question you need to ask is, what is this part's job in the real world? In this video, we're going to focus on this blue plate. Let's look at the big picture, though, of what this blue plate is doing. We have a drive shaft here that runs through this mounted bearing. The mounted bearing is attached to our blue plate. Then on the end of that drive shaft, we have a timing belt pulley with a timing belt that goes down here to this gear motor with a larger timing belt on it. And we're just going to imagine that over here we have a tensioner to keep this belt tight. We have a couple of uprights here, and they provide the space for the gear motor to sit down below. So our blue plate is just up here to hold this bearing in place, mounted to these uprights, and give a support for that drive shaft. Drive shaft goes off wherever it goes into space. That doesn't matter for this demonstration. This is all just made up anyway. But what matters is that this bearing plate is here to hold up that bearing centered over the motor. The second question we need to ask is, how does this part interface with the rest of the assembly? Keep in mind, we're focusing on this blue plate, so we're going to look at all of the things that it touches and how all of these other parts relate to it. The main thing, as we said, that it is doing is holding up this mounted bearing. That bearing has a bore through the middle that the shaft is mounted to. So we can see from the back here the 2 tapped holes in this plate. We have the clearance hole for the shaft centered between those 2 tapped holes, and that's going to be important that the geometry of this part, the center hole for the shaft and the 2 clearance holes for the screws, they have a relationship that matters, and we need to maintain that relationship as we go through the design of this plate. The other considerations for this blue plate is that it attaches to these uprights. These uprights have tapped holes in them, and we need to be sure that the tapped holes in the uprights align with the clearance holes in this plate. There are some things that we could do at the assembly level to make sure those always work together, but for now we're going to keep it a little bit simpler and just work within this blue plate. The third question we need to ask is, how does this part relate to itself internally? And there are a couple of considerations as we look at this. If we consider the corner holes, look at those 4 holes. They relate to each other just within that feature, and that these 2 top holes are horizontal to each other, directly across from each other, as are the 2 holes at the bottom. And then we have the holes down the sides, that this hole needs to be directly above, vertical from this hole. But these holes also have a relationship to the edges of the plate. I need this hole to be a certain distance off the edge of the plate, and that's going to be the same distance down here. Likewise, we have these holes from the edge down the side, also the same distance from the top. But also we need to look at the center holes here. We have the shaft clearance hole For this demonstration, I want to keep it centered on the plate. So it's going to have a position relative to the top and bottom of the plate, as well as the sides of the plate. And when we look at then the tapped holes that secure that bearing to our plate, they need to have a certain relationship to each other. They need to be a certain distance apart, which is going to, of course, match the distance between the holes in the bearing. But then they also need to align to the position of that center hole. If these two tapped holes lose their position relative to the shaft clearance hole, then the assembly is not going to go together right. So finally, the fourth question we need to ask is, what happens if something changes? What happens if I change the size of the plate? Currently it is 6 by 12, and we have to look at what happens if I decide I need to make this part bigger. What happens if I need to change that shaft position? What happens if I need to make these uprights thicker, and I need to change the position of that tabbed hole? What happens if I need to change to a different bearing that has a different hole pattern, a different spacing between these holes? Well, let's go in and make some of those changes and just see what happens. Now, if I need to make this plate wider, suppose I ended up with a bigger gear motor down at the bottom, or I needed to make more space. What if I go in and I need to make this, let's say, 16 inches wide? Look at what happens to my plate. I no longer have these two holes over here next to the edge. What if I needed to go smaller? What if I ended up with a 10-inch plate? Now I've got holes over here that have disappeared. All of this is no longer on center. Let's hit undo a couple of times to get that back to where it was. Let's change something else. What if I change the position of that shaft? Let's say I just need to move it to the left an inch, move it up an inch. Now we got those tapped holes moved a little bit, but they did not go everywhere they needed to go with that center hole. So we see what can happen. Some things fall apart. If I want to come back in here and fix these, the way I've got it set up now, I've got to go in here, get back to this, see all kinds of weird things happen. I need to go in, change that dimension, to try to get things aligned back the way that they were. So what we want, the kind of bulletproof CAD models that we want, the way we want to use design intent and a thoughtful process in our design, is to make it so that if I go in here and make any of the changes that we've been talking about, everything updates smoothly, automatically. We don't lose any features, nothing breaks and gets weird. So let's take this step by step and see how we can make this a better design. Now, as you are designing, a good place to start is with the main thing that your part does. And in this case, the main thing our part does is support this bearing and provide a location for that shaft. So that's where we're going to begin. After we have the dimensions down, we don't need to do anything here. We're going to leave this at our 6-inch by 12-inch rectangle. And the next most important feature should be our shaft clearance. So I'm going to move that up the list. You can drag and drop these features and go up the list. I'm going to put the shaft clearance right below the main body of the plate. Now let's edit this sketch and look at how our shaft location is dimensioned. Knowing that my plate is 12 inches wide, I made this 6 inches wide. If I change that, it moves around. But what really matters to me is that this hole be centered on the part. So I'm going to add a dimension. It's going to say it's over constrained. It's a driven dimension. And that's fine. You can turn off that notification, but we'll leave it on for now. We get that driven dimension in parentheses that says I can't change this dimension. I can't edit the size of the part from here. It's just telling me that my plate is 12 inches wide. So this dimension, now for my hole location, I'm going to come up here and just click on that 12-inch dimension and say divided by 2. Now I have a function here that is determined by this number up here. It is this dimension divided by 2, which is going to keep me centered on that plate. Let me make one little note here. I could use a vertical constraint here to here, and that will keep me centered. But just in case I ever need to come back in and change this dimension, I can take what is currently that formula, I could take it back and I can just put in a number there and get it to a different location if I need that. But I'm going to leave that right now as half of that 12-inch dimension. We will do the same thing over here, accept that driven dimension, and do that 6 inches divided by 2. And that, can't really see it, there it is. That puts our whole location centered on the plate, which as we have it set up just happens to be on the origin of the sketch as well. So that guarantees that no matter what, my shaft clearance hole is going to be in the center of the plate. Now let's work our way up a little bit. I'm going to move the bearing mounts up to just below shaft clearance because the location of the bearing mount tapped holes relate to the shaft clearance hole. So let's go in and edit this sketch. Currently, what I have is 1.75. That is half of the bearing spacing, of the hole spacing in that bearing, off of the center of that circle. But I want to do this a little bit different. I'm going to delete all of those dimensions. I'm going to add a horizontal constraint, that point to the center of my circle, that point to the center of my circle. Then I'm going to come in here and add this dimension, still sitting on 3.5. That is the spacing of the screws in the bearing. And then I'm going to do this formula again, use the 3.5 dimension divided by 2. So that way, no matter what happens to this dimension, if I had to go in and use a larger bearing or one with a different hole spacing, no matter what, those two hole locations will always move with that number, but also stay centered around that center hole. Finally, let's take a look at these corner holes and look at a better way to set them up. Put a bunch of dimensions up here. Look at this 11.5-inch dimension. Knowing that my plate, again, is 12 inches wide, and I want a 1/2 inch over here, I put in a dimension from this far edge. But that does not serve me well, neither does this 5.5-inch dimension over here. I've got a 1/2 inch here and a 1/2 inch here. I don't need that many dimensions, so we're going to clean up, get rid of some of these, and see a better way to do this. Now think about what matters to me. I know that I always want this hole to be directly above this hole, so I'm going to apply a vertical constraint there to there. I'm going to do the same thing on this side, vertical constraint, that point to that point. Now I'm going to use a horizontal constraint there to there, and a horizontal constraint across the bottom. Now look at what happens. If I move this point, see the other ones move with it. So now I just need a couple more dimensions. I'm going to make this dimension reference this 1/2 inch up here. So that keeps us the same distance off the edge no matter what. And then from the bottom, I'm going to reference that one so that our dimension off the top and bottom are independent from the dimensions off the side. All right, finished that sketch. And now that I've gone in and made all of these changes, let's do some tests. Let's change some of the information and see how well this model updates. Let's go back to our plate size. Let's take our 6-inch height, make it 8 inches. Take our 12-inch width, we'll make it 14. Finish that sketch. So far everything is good. That center clearance hole stayed centered, and the mounting holes around the edge moved the way that I wanted them to. Now let's go in and work on the shaft clearance. Suppose I change this dimension. So let's keep it centered left to right, but let's make it be just 3 inches from the top. Finish that, and now everything moved with it. Let's move the bearing mount holes. Say we got a new bearing, and these need a 4-inch spacing. They stay centered. That looks good. Everything moved. Let's make one last change. Let's say our uprights ended up being thicker than what we originally had, and we want to keep that hole centered on the uprights. Currently, I've got a 1-inch thick plate for the uprights, so I wanted a 1/2 inch. But let's say we went thicker. I need to make this 0.75. See how this updates. They all 4 moved in from the edge, but kept their 1/2 inch distance from the bottom. Let's change this one now. Suppose I want to move them down. I want them all 1 inch from top and bottom. Finish that sketch and everything moves with it. Of course, at this point, I haven't actually made those changes in my assembly, so that's going to make things not line up. So let's go back and quickly put all this right back to where it was. Fix the plate size. Fix that shaft clearance hole. It's going to be that divided by 2. Bearing mounts back to 3.5. And the corner holes, mistyped that number. 1/2 inch there, 1/2 inch there. Everything's back where it belongs, and everything looks good in the original assembly. So there we have a relatively simple demonstration of design intent. The main thing is to think through what the part does in the real world, how the part relates to the assembly and to itself. And when you work through a design that way, you're going to get something that updates a lot better, that doesn't fall apart when you change one little dimension. Keeps everything the way that you want it, keeps all the relationships consistent, and makes your updates a lot easier and saves you a lot of time changing dimensions when you need to make one little change. If this has been useful to you, I would appreciate a like on this video. Please subscribe to the channel if you have not already. I am building up a library of Inventor tutorials as well as design philosophy focused videos like this one. So go check out the main channel page to see more of those. Thank you so much for watching. Have a great day.